Hello class, this is our summary of MathPath Week 1, or the first assignment in the MathPath. And just wanted to review this stuff real quickly and give a little wrap up since we're not doing it in the main lecture because many people aren't doing the math part of class. So we had 3 rules to our algebra game. Rule 1 was as long as you did the same thing to both sides of the equal sign, you could do whatever you want. Rule 2 was when you take the square root of things, there is a plus answer and a minus answer. That's going to be really important in our next unit on waves and coming up with the wave function, because we're going to see things are a little bit broken. And rule number 3 were any algebra rules for numbers also work for units. So just a little bit back into the history of things, Isaac Newton didn't actually say force is equal to mass times acceleration in his Principia. He said force was proportional to mass and force was proportional to acceleration. But we know that as Newton's second law of motion, F is equal to m times a, which is something that we are going to use that we used in this first homework. We also used Newton's law of universal gravitation, which is that the particular force is equal to mass times acceleration works for all forces. When you're looking at a particular force and you're trying to figure out how much that force will be, this particular force due to gravity is equal to the gravitational constant, that's the big G, the mass of one thing times the mass of the second thing, divided by the distance between them squared. So we show this is r squared here, this is d squared in our homework. Now, we talk a lot in class about the fact that acceleration is any change in velocity. Well, velocity is speed and a direction. There's a number part and there's a direction part. When you change velocity, we talked in class about how you can change the direction or you could change the number part, and both those changes were an acceleration. So obviously there is a number part and a direction part to the acceleration. We mentioned a couple of times that there's a particular name for something that has a number part and a direction part, and that is a vector. The problem when you look at this particular way of looking at it here is it says F1 is equal to F2, and yet you look at these and they are pointed directly at each other, right? So they're pointed in the opposite direction. And this little symbol is the symbol for a vector. So really up here, I should say the force is equal to mass times acceleration, because acceleration is a vector. Now here, this is obviously not true that the force this way and the force this way are equal if you're talking about the vector, because the direction is different. What they actually mean here is the size. And to make that more clear, it's actually the way that they've written it, you could kind of be nice to them. If I were grading their test, I would still take some points off for not being clear. But they that they are talking about when they put this bar around it, this means I'm just talking about the number part of that vector. All I want is the number part. And this number part of the force of the earth pulling towards you and the number part of your force pulling towards the earth are the same, and they're just going in opposite directions, right? The earth pulls you towards it, you pull the earth towards you. That's the way it goes. Okay. And this is equal to a big old constant G, the mass of, in our case, the Earth, and the mass of us, which is 2, divided by the distance between a square. But these can be any two masses, as we saw in our homework. So how does each ball accelerate towards the Earth when we are dropping the heavy and the light ball from the towers, right? So we can look at the heavy one first and say G is a constant we can look up. You can actually Google it, it comes up just fine. M1 is the mass of the Earth in kilograms, so this is the mass of the Earth down here. M2 will stay an algebra mystery for now. Could be any of you students in there. And r will be the distance from the center of the Earth to the surface plus 1.5 meters. Wow, 1.5 meters is actually really tall. But, right? So, how tall is 1.5 meters? 1.5 meters to feet. Let's see. Oh, 5 feet. All right, so 5 feet, not too bad. Okay. So we measure the center of mass is, or we calculate all of the mass being, it's like we can consider the mass of the whole Earth to be a single point source. This is just for estimating. Just for estimating. If you're trying to find the local gravity near you, you have to do something else. But you assume that all the mass of the Earth is located here. That's the center of mass. And then you take your height there. And so our distance will be the distance from here to the surface. And then you're above the surface. So you're like 5 feet above the surface. That would be your center of mass. That would be really tall because that would mean that you're 10 feet tall. But okay, anyway, this is what we have. All right. So, or you're standing on top of something. All right, so here we go. So we have the force due to gravity is big G, m1, m2, divided by r squared. We plug all that stuff in. Here's this is 1.5 meters added. This is the radius to the Earth. Okay, we can eliminate, we'll do the units first. We eliminate, the m3 goes away because I have an m2 here. So I'm just left with an m up here for meters. The kilograms, I have one at the top, one on the bottom, so the kilograms go away. And what I'm left with is the force due to gravity is 9.822 meters times m2 divided by s per second squared. Okay. So it doesn't matter. M1, oh, wait, so we haven't gotten to it doesn't matter. So the force due to gravity is 9.822 meters per second squared times m2. Force equals mass m2 times acceleration. So the acceleration I'm experiencing, if I'm m2, is my mass times times my acceleration. If I put that side on one, if I put that on one side and this on the other side, the m2's cancel out, and my acceleration due to gravity is 9.8 meters per second squared. And this is why we use this number, 9.822 meters per second squared, as an estimate of the acceleration due to gravity of anybody who's on the surface. Anybody who's on the surface. Oh, the 822 comes from the 1.5 meters. We really estimate it as 9.8 meters per second squared. Okay, so heavy or light doesn't matter. It's nice that it works out in the math. In your homework, we got to a point where the force due to gravity is equal to the mass of the volunteer times the acceleration. And this acceleration was going to be different than Earth's acceleration because we're using the sun instead of the Earth. And the gravitational constant stays the same. This is the same for the entire universe. Every time we talk about force due to gravity, it's the same constant. And this is the mass of the volunteer divided by the distance between them squared. And then we canceled out because we can divide both sides by the mass of the volunteer. The mass of the volunteer went away, and we could figure out the acceleration of the volunteer to be equal to the gravitational constant times the mass of the sun divided by the distance between the volunteer and the sun squared. Now, when I say heavy or light, it doesn't matter. That means it doesn't matter for my volunteer. It doesn't matter for the 2 balls I'm dropping on Earth. It does matter for one of them. I'm measuring these things relative to a frame of reference, and the frame of reference right now is the sun. If I drop the heavy and the light ball on the moon, they will both fall towards the moon at the same acceleration, but that acceleration will be different on the moon than it is on the Earth, and it's different near the sun than it is on the Earth. So when I say heavy or light, I mean considering 2 objects that I'm dropping towards the same object. Heavy or light does not matter. Okay. Okay, I'm going to have to continue this in our next video. See you next one. Bye.